Now, when we're talking about the large growth of any technology, we have to think of how sustainable this growth is. Do we have the resources? Do we have the human potential that we need to do that? And one way to look at it is life cycle analysis. It is a framework for studying sustainable development. What do we mean by sustainable development? Is a development that meets the needs of the present generation without compromising the ability of future generations to meet their own needs. So it has transgenerational and it has global components. We cannot really exhaust all the resources that the future generations need, and we cannot really exhaust the resources in one place that other places on the planet, other people on the planet need. Now, with this in mind, we look into sustainability in our work at the Center for Life Cycle Analysis along three major components. We call those major or fundamental pillars of sustainability. In energy and also in development of any new technology, how affordable it is, not only for the rich ones in America and in Germany, for example, but for the developing world, how affordable a new technology is. If we have enough resources in terms of materials, land, water, human labor, and so on. And we obviously are interested in the lowest environmental impact. I cannot say zero because I don't think there is a zero environmental impact on anything that actually needs to be developed in large scales, but we're looking into the lowest environmental impact. So in that last pillar, life cycle analysis, it is the tool that will give us more insights, the more complete picture. Life cycle analysis starts from the cradle. The cradle is the earth, from where the resources will come, and ends at the grave, or perhaps at another cradle, if at the end of the life we can recycle materials back into new materials. So it goes through the different stages: the materials extraction, the processing, refining, the development, the manufacturing of the pieces, the manufacturing, the installation of the system, the operation, and so on, until the end of the life. Now, I will give you the example of how this is applied and what results we get in a nutshell in new solar energy technologies in photovoltaics. All the stages, so starting again from the raw material extraction into the processing, because we need very pure materials in photovoltaics, as pure as 99.9999 in order to have the electrons to travel into the crystal without any interference. So it takes some energy to do that. We have to account for all of this. Then we manufacture the cells, we manufacture the big panels, we manufacture the structures, all these frames, the supports, and everything. We have them operated for 20, 30 years. Perhaps we need to clean them, or we need some maintenance. At the end of the life, we have to do something about this. We recycle as much as we can, obviously. We may have some waste. So we have to account for every stage in this life, and quantitatively, we will be looking into material inputs, emissions, material outputs in all pathways, into the air, the water, the solid pathway, the earth pathway, and also energy. That Q that you can see on this picture is the energy. Of course, energy can be the reason for a lot of pollution. So if we don't use photovoltaics to produce photovoltaics, but we use fossil fuel to produce photovoltaics, we're going to have some pollution because of the fossil fuels that are used in the manufacturing of photovoltaics. Keep this in mind. So the metrics to see the performance there, what technology is better, and to compare different technologies among themselves and with other energy technologies, because the electrons may not have DNA. So let's say photovoltaics will produce electrons, wind will produce electrons, but also natural gas and coal and nuclear will produce electrons. So we have to compare the different technologies that produce those electrons that we need so much. The basic metrics are one, energy payback times, how long it takes for the system in operation to produce the energy that has been used in the whole life cycle or is going to be used. Greenhouse gas emissions obviously is very important. We want photovoltaics, we want clean renewable energy because we wanted to stop the large emissions in the atmosphere of greenhouse gases, resource use, materials, water, land, and environmental health and safety risks. And I outlined there the statement that there is not a zero impact technology. So we have to compare. Nothing is zero. We have to compare with other energy-producing technologies in terms of these metrics. So the basic metric, energy payback time, that it gives in a number of years how long a system should operate to produce all the energy that has been used in the life cycle. It is a relatively long equation. It has a sum of the energy used in every stage of the development of a system and is divided by the energy that is produced. So you can see the different components there. And if we take in the life expectancy, how long this system will operate, then we get what is called the energy return on energy investment. The acronym is EROE. So it is the lifetime divided by the EPBT, that is the energy payback time. So if the energy payback time is 1 year, the meaning is that in 1 year it produces all the energy that has been used in the whole life cycle. We account in advance also the energy that will be used at the end, at decommissioning. Now, if the system will operate for 30 years, the EROE will be 30 divided by 1, that will be 30. If the system produces all the electricity in half a year, the EROE will be 60. Just as an example, energy payback times in different technologies that they range from about 1 to 3 for operation in Germany. There was the biggest market early on, but Germany does not have a lot of sun, so 1,000 units kilowatt hours per square meter per year. If we have the same system in the north of Chile, where the sun up towards the Atacama Desert is 2.5 times higher, the energy payback times, they're reduced by a factor of 2.5. The same approximately could be in our southwest. So energy payback times as low as a half a year, perhaps to a year. And you can see different numbers there because we have different technologies, and the silicon technologies need more energy, and we have different efficiencies. So the energy payback times is a function of 3 things. One is how much sun we have. 2, what technology is used, because different technologies have different energy burdens. And 3, how efficient is the technology. Now, greenhouse gas emissions normalized per electricity output per kilowatt hour, they are not zero, but because we're using some fossil fuels into the production of photovoltaics, nothing is emitted during the operation, not greenhouse gases, not toxic gases, nothing. But because we use some fossil fuels in mining, in smelting of the metals and so on, and in manufacturing of the cells and the modules, we have some emissions. The numbers are down there, like 14 and 28 for technologies as of about 5 years ago. But now they're even better. But those numbers, they're better than nuclear in the United States and 2 orders of magnitude lower than those from fossil. You can see the yellow sections of the bars there in coal and natural gas and petroleum combustion. Their emissions, CO2 emissions, because of the combustion. And then you have emissions in the extraction of the resources, in the fuel and so on. You have 0 of those in photovoltaics. The only emissions there have to do with the production of the materials in photovoltaics, not emissions related to fuel extraction, no emissions related to during the operation. Now, we're looking also into resources, land, materials, water, and so on. And this picture says the whole story, that photovoltaics, if we put them at the top of a roof, they don't take any more land. If we put those on the ground, and we need that for large systems, and we need a lot of these big units in places that they have a lot of sun. For example, in the United States, we need large installations in our southwest if we have to have solar electricity in, for example, in the northeast, in New York, in the winter. Because there is plenty there in the winter, but there is almost very little in the winter in the northeast. So we need those ground installations that are the cheapest, and they can provide a lot of electricity in addition to the many dispersed on rooftops. This picture shows that the land use is ecologically very friendly, obviously. Now, some will think that PV uses a lot of land, and it is a myth. It has been propagated for years, but it is really a myth, because if we look at the whole land that is used, for example, in the coal life cycle, and of course, we have to account for the land in the mining of the coal. In the United States, about 75% of the coal comes from surface mining, use a lot of land. So if we account for all the land with the life cycle analysis tool that we use, then photovoltaics use less land than coal, comparing with average in the United States. Water. We know that droughts have increased in arid areas. We have flooding in other areas. All these are the extremities that they are very well predicted by our climate change models. But water is a problem, especially getting into higher power, into higher energy growth. Water is a problem, and thermoelectric generation needs a lot of water for steam and for cooling. Photovoltaics and wind don't need any water. Even when you clean them, and in many areas they don't need any cleaning, they don't need water, they can be dry cleaning. It's very, very little water. So it saves water, which also it is a challenge in scenarios of population growth and so on. And not only that, but also solar energy is so affordable, it's so inexpensive now. It can be used to produce water. We can produce water with desalination of seawater, desalination of brackish water, or cleaning of waste treatment water. We can produce the water that way if we have cheap energy. The cost of seawater desalination, it is by 50% is the cost of energy. So affordable solar energy, it also gives a solution into the water problem. And obviously, it is the lowest environmental impact type of energy and is getting less and less expensive, and obviously is very reliable. So I hope that this was intriguing enough for you to start looking perhaps for more information on life cycle analysis. And for this, you could use the resources at Columbia University. In the Center for Life Cycle Analysis, we have a website that you can see on this slide, and a bibliography of relatively simple articles that they can give more resources, they can lead to more resources if you wish. Thank you.